It's an honor for me to be here today. This is such a wonderful institution that's at the University of Michigan, Saturday Morning Physics. And I'd like to thank the people in this audience who helped make this possible through your attendance and other contributions that you make. And I just am excited to tell you about mass today. It's a few years ago, I wouldn't have been excited to tell you about that. If somebody said, give a talk about mass, I would have said, what would there to say? I don't know what to say. Now we have so much to say about it because of recent developments at CERN primarily. Now, mass and weight has been a part of human interaction and human knowledge for as long as recorded history speaks of it. Ancient Egypt made small figurines out of metal that acted like counterbalance weights for measuring grain and other things. On this upper left-hand corner on this slide, we see in a vase from 5th century BCE, the Greeks weighing various things, various merchandise, and making sure that they were on the up and up. And they made these standard weights. In the bottom left-hand corner are standardized weights in ancient Greece for measuring, so that merchants couldn't cheat you on whatever it is you were purchasing. And in the bottom right-hand corner is our present-day standard of mass. This is the 1 kilogram platinum bar in Paris. And you've probably seen in the news recently that the platinum bar is gaining weight. So it's, I mean, like everybody, it gets older, it gains weight. And so they've had to do very careful cleaning of it because it's the standard by which all other weights are compared to. So I'm not going to talk about that platinum bar in Paris. I want to show you, I want to first make sure that we understand the difference between weight and mass. And in our English societies, we always talk about weights. And when I was in Europe, everybody talked about mass. And I have two columns in the bottom of this slide that tell you the difference between the two. And that equation also tells you the difference. Weight is equal to mass times the acceleration due to gravity. G is just some constant. And we talk about mass and weight on the surface of the Earth. And so the acceleration due to gravity is about 9.8 meters per second squared in the metric units and 32 feet per second squared in English units. So when we talk about our weight, we say 200 pounds or 150 pounds or whatever we are. So that's in red there under the imperial units. But a few of us know that that's equal to 6 slugs. So it's no wonder we call it pounds, right? It's go to the doctor and say, I'm sorry, I'm 7 slugs now. It doesn't sound very good. So we use the weight system. And slug is actually a Middle English word, slugga, and it comes from the Scandinavian slugga, that means sort of heaviness when walking, sort of sluggish and heaviness in walking. So the more mass you have, the more sluggish you are, and the more slugga you have. So that, we don't use slugs, but maybe in the future, maybe you'll go home and use slugs. You can change your scale to that. In the metric units, it's mass. We talk about, we weigh 80 kilograms or 70 kilograms or 100 kilograms. And very few people who use the metric system know that their weight is measured in newtons. So the mass of 90 kilograms times the acceleration due to gravity, 9.8 meters per second squared, gives you close to 900 newtons. So weight is place specific. Your weight is different on the moon than it is on Earth because g, the acceleration due to gravity, is different on the moon than it is on Earth. So your weight can fluctuate. If you want a really low weight, go to the moon. But your mass is unfortunately going to stay the same. And that's why we consider mass more fundamental than weight. It is an intrinsic property of an object and a body is its mass. So we are going to discuss mass, and at times I will use the word weight, perhaps colloquially, but really the fundamental object under consideration is mass. Now, there's been many questions regarding mass. What makes some things heavier than others? And the ancients were very mystified by this. And even the not-so-ancients, a few years ago, even dozens of years ago, people didn't have a good idea on that. For centuries, it was said that there was more stuff. If you had more weight, it meant there was more stuff. And so that doesn't sound very sophisticated, but if you call it in Latin, it sounds very sophisticated. Quantitas materiae. So then people think, well, I know what I'm talking about. I just said it in Latin. But you don't really know what you're talking about. And when you say quantitas materiae. So there's very little understanding of what mass meant and how we achieved it, how we have it. But over time, physics and chemistry elucidated it. Newton's law was a key step in our understanding of the operational definition of mass. So his second law was F equals ma, force equals mass times acceleration. And sometimes more useful written, mass equals force divided by acceleration. So in some ways you can measure the force, you can take a spring and then define what force it has at some displacement, and then put different masses on that spring, let go and watch it accelerate and measure that, and that can tell you what the mass is. The heavier the mass, the less it wants to accelerate. For a very light mass, it wants to accelerate very quickly. And so this was a nice operational definition of mass. It fit into these equations of Newton very well, and we went centuries of not really knowing what mass is, but using it, okay? And I mean, we go through our lives using a lot of things that we don't understand, and it's sort of an embarrassment to physics that for hundreds and hundreds of years we used this concept of mass, but we didn't really know how it came about. But our concern today is not going to be why things have different masses and mass densities. So I'm not going to talk so much about the chemistry of a feather versus a hammer. I'm going to talk about why there is mass at all. What gives rise to mass at all? And the different approaches in the last few decades on this question and what we've learned. So the first place you should go is hydrogen atom. And hydrogen atom is my favorite element. Hydrogen is my favorite. Some people are really partial to oxygen. There's this detail about keeping them alive and so on. But oxygen is only 0.1% of our visible matter universe. It's a tiny fraction of things. So we're really quite selfish when we're so partial to oxygen. Hydrogen, I'll tell you, there's two things I really love about hydrogen. One is it's 75% of the visible universe is hydrogen. The sun is burning hydrogen. It's really important, hydrogen. The second thing I love about hydrogen is it's the first non-trivial calculation that students can do in quantum mechanics. So quantum mechanics is this really weird theory of physics, and there's a lot of qualitative things said about quantum mechanics, and students can do very detailed calculations for homework assignments on many things that are not really realistic. They're sort of arbitrary, strange setups that we put in front of the students when they first begin in quantum mechanics, and they can do calculations and they can say, the universe is not like this, but if it were like this, this is the answer you would get in quantum mechanics. Hydrogen is the first really important problem that's realistic that they can solve in quantum mechanics. And I happen to be teaching quantum mechanics this term, and we just did hydrogen last week. And the students are very excited about that. So we solve hydrogen atom in our classes, and so we are going to talk about hydrogen here because it's the first good place to talk about mass. Hydrogen is a bound state of an electron and a proton. So an electron has a very small mass, which we call 0.5 MeV. 0.5 MeV is equivalent to about 10 to the minus 31 kilograms. Since physicists don't like to carry around 10 to the minus 31 factors, we define a new unit of mass, which is called the MeV. Okay, it's a unit of energy mass. So 10 to the minus 31 kilograms is 1 with 31 zeros lighter than that bar of platinum in Paris. Okay, so electron is very, very light. And the proton is about 2,000 times heavier than that, 938 MeV. And the hydrogen atom is not quite the sum of the electron mass and the proton mass, because there's some energy of binding between the two, the electron and proton. So this mass is a little bit different. It's actually a very tiny bit different. It's 10 to the 8 times tinier difference in mass than the sum of the electron and the proton. So it's very close to the same mass. So the question really is, how did the electron get its mass, and how did the proton get its mass? Okay, so that's the bulk of the question of how does hydrogen, the element in the air and what's burning the sun, how did hydrogen get mass? So Einstein taught us that there is a relation between energy and mass. So this is the famous equation, E equals mc squared, where E is the energy, m is the mass, and the proportionality constant between the two is the speed of light. The speed of light is 3 times 10 to the 8 meters per second. So it's just a constant, it's just a number. And there's direct interchange, direct relation between energy and mass of an object. But for us, there's a better way of looking at this equation. And it's just to do division on both sides. And we can rewrite it as mass equals energy divided by the speed of light squared. This was, as far as I can tell, the original way Einstein intended for us to think about this equation. And I looked up the original article from 1905 where he introduced this relationship. And it's there in yellow on the slide. And the translation is there in red just below it. The title is, Does the Inertia, or mass, that's what they called mass back then, was basically inertia, of a body depend upon its energy content? So I think there's two really interesting parts about this title. One is, I'm really focused on the question mark. So this is 1905, Einstein, and it is a question. He doesn't know the answer, and nobody really knows the answer to that question. There's a question mark in the title, and he's trying to answer it. And he says, well, if a body gives off an energy L in the form of radiation, so that's a photon, that's sort of very high energy light that comes off of a body, then its mass is diminished by that energy divided by the speed of light squared. This is how he intended to talk about mass. So you have a body here, maybe it's an excited hydrogen. It radiates light, and it goes to normal hydrogen. That is less massive. And Einstein wrote this in 1905. And I think there's another interesting part about the question mark. We physicists tease people who write papers with question marks because there's a theorem that if you write a paper with a question mark, the answer is always no. Okay? And generally, scientific papers with a question mark is somebody who thinks that the answer is yes, and they work really hard for 6 months, and the answer turns out to be no, but they don't want all of their work to go to waste, and so they write the paper anyways with a question mark. Okay? So Einstein wrote his paper with a question mark, and the difference between Einstein and us is his question marks are answered with a yes, and ours are often answered with a no. Okay? And the answer is definitely yes for much of physics. The mass does depend on the energy content. So let's try to explain mass by this bundle of energy. So there's some bundle of energy, and that is sort of acts equivalently like mass. So let's start with the electron. Well, with the electron, we have smashed it, we have banged it, irradiated it, we've waterboarded it even, we've irradiated, tortured, hammered, everything you could imagine to an electron, and it stays intact. There is no sign that the electron is divisible. It looks completely point-like. And I didn't know how to make a point-like particle with no spatial extent on a slide. And so I just put this little dot here, which is infinitely too big. And I say the electron, it has no internal extent or structure, and therefore no internal springs or balls or chains or anything that you can store energy inside of to give it mass. Its mass just is. Okay? And we're stumped on the electron mass. Okay? So its mass just is. So from our standpoint, the electron is an elementary particle with elementary particle mass, and its mass explanation is not E over c squared, but rather something else. So we have to put that question on a back burner for a while. We don't know how electron got its mass. Let's try the proton. Can its mass be explained by E over c squared, like Einstein thought that things should be explained? Indeed it can, mostly, and you will see why I use the word mostly in just a minute. The proton does have extent. It does have structure. We learned in the 1970s that it was made up of quarks. So the proton is not an elementary particle. It's made up of quarks, and it's primarily of 3 quarks: an up quark, 2 up quarks, and 1 down quark. And to get the charge of the proton, you sum the charges of the quarks. So 2/3 plus 2/3 minus 1/3 is equal to 1. And so the proton has charge 1. And the proton is a bound state of these 3 quarks. So the energy dynamics of this bound state is what constitutes the majority of the mass of the proton. I said electron here, but I mean proton. So the up quark has a mass of only 3 MeV. The down quark has a mass of only 5 MeV. So you think, well, the mass of the proton is twice up quark plus down quark. That's the mass of the proton, right? Well, that's only 11 MeV. Somehow, when we measure the proton mass, it's 938 MeV. There's a huge difference between the two, gigantic difference. And so the elementary particle mass contribution to the proton mass is very small compared to the E over c squared contribution. Now, what is this E over c squared contribution? So there's a conundrum here. So in hydrogen, we said that its mass is less than the sum of the electron and proton. There's very little difference between the mass. It's sort of inconsequential almost, the difference in mass between the electron plus proton compared to hydrogen. And that's a bound state of electron and proton. The proton, on the other hand, is a bound state of quarks, but its mass is much greater than the mass of the constituent particles. So why is that the case? Why is the mass of the proton so much greater than the sum of the constituents? It doesn't seem to make sense. This is another question that confounded people, and still the details are tricky. If you want to win $1 million, you can dot all the I's and cross all the T's on this explanation. okay? Because it's not fully explained from first principles, but we know what the answer is. We just can't quite mathematically prove it. And the answer is that quarks feel the strong force. Unlike an electron, which feels just electromagnetism, the quarks are bound together by a new force that we call quantum chromodynamics, or the strong force. And it's qualitatively different. You should think of the strong force as two quarks being attached by a spring. And if you've ever dealt with the spring and pulling it apart, you know that as you pull it apart further and further, the force you need to pull it apart even further is greater. The further you go out, the greater force you need to pull it even further. If the spring is slack, it's really easy to pull it apart. If the spring is from here to that door and I want to pull it a little bit further, I can't do it. I need the whole auditorium to help me pull it. And this is a weird part of quantum chromodynamics. And therefore, this difference is that the force increases with distance, whereas in electromagnetism and in gravity, the force decreases with distance. Okay? So there's a difference in sign between the forces required at large distances. And here is the explanation. It's a bit tricky, so I'll try to go somewhat slow. This increasing force with distance tells you that the quarks must be confined to a small space. No quark is allowed to just go arbitrarily far from another quark because the spring is just too tight. So all these quarks are confined within a tiny space of 1 femtometer, 10 to the minus 15 meters. So very small space. Okay, so that's fact number one. Fact number two is that Heisenberg's uncertainty principle, which you can derive from quantum mechanics, this is not controversial. Understanding the first part is difficult. It's not controversial, but it's mathematically very difficult. The second part is not mathematically very difficult and was known in the 1930s, 1920s. Heisenberg's uncertainty principle says that you cannot know the position and the momentum of a quantum particle perfectly. There is some uncertainty necessary in quantum theory. And this is the eerie part of quantum theory, is that you can never know position and momentum simultaneously. Well, if I know that I'm confining quarks to a tiny space, then it means that the uncertainty in its position is very small. So this uncertainty in position is very, very small. And so therefore I have to support a very large uncertainty for momentum. And momentum is proportional to energy in this relativistic limit. So momentum is proportional to energy. From this Heisenberg's uncertainty principle, I know to localize this particle to a small space, I need lots of momentum. I need to be able to support lots of energy for this. So that, if you do the calculations on this, it comes out to be hundreds of MeV of energy needed to localize it to 1 femtometer volume. So if you do the calculations even more precisely, you get out an answer of 938 MeV, the proton mass. So this is a large amount of energy all packed into a tiny space. And this is the confinement problem of quantum mechanics, quantum chromodynamics, and it explains 99% of the mass of the proton, and therefore 99% of the mass of the hydrogen atom. So it's this kind of bundle of energy inside the proton which is explaining the vast majority of visible mass of our universe. So let's call that the energy bundle mass. Okay? Just made that term up for fun. So it's bundle of energy in a localized place. So only 1% of the mass of matter that we know about comes from the it just is type, where we don't know how it comes about. Electrons and quarks has an intrinsic mass that we just don't know where it came from. Let's call that elementary particle mass, electrons and quarks. So in the previous few slides, we explained energy bundle mass. Is there an explanation for elementary particle mass? In other words, can we explain how electrons get mass or how quarks get mass? And the answer, as of last year, is yes. Okay? This is the excitement of the last year. First, let me introduce you to all of the elementary particles. All of nature, visible nature, matter that we know about is made of this small set of particles. It's a very exclusive club. The first column is the up and down quarks, which make up the proton and the neutron. And this is the electron. And this is the neutrino that comes out of radioactive decays. Okay? So this is the first generation of matter particles that make up everything we see around us. Makes up this table, makes up me, makes up most of you, every one of you. And these are the force carriers. This is a photon for electromagnetism. This is the gluon, which makes up that spring that keeps the quarks tied together. And this is the W and Z boson, which is very instrumental in the radiation, nuclear radiation, for example. And then there's exact copies of these particles. There's only two more generations of exact copies. But exact copies, the only difference is their mass. Their charges are the same, their spins the same, everything is the same about these different two other generations of particles, but their masses are different. And here's a slide that graphically shows you what the mass is. So here's the mass of the up quark. The size of the ball is proportional to the mass. Okay? So the up quark is a small mass, the down quark is a small mass, the electron's even smaller mass, the neutrino is extremely small mass. It's not zero, but it's extremely small. And this is the second generation, and this is the third generation. Heavier and heavier masses. And all of these particles, the mystery of how they get mass is the same as the mystery of how the electron gets mass. And there was no explanation of it. We knew they had mass. We didn't know why. Okay? So, how do they get mass? This is the answer. This is what we learned last year. Okay? I want you to reflect on this for 5 seconds. That's the answer. You know, when physicists try to explain the Higgs boson and why it gets mass, it's really difficult. I hope you'll excuse mixed metaphors that I will give in the next few minutes. But I think the best way to think about it is a field that permeates all of space. So we are surrounded by the Higgs field. We are also surrounded by the electron field. And we are surrounded by the top quark field and other fields all around us. But there's a difference between the Higgs field and all other fields that we know about. And that is, it has a non-zero value everywhere. The electron field is zero everywhere. Nothing feels the electron field. Every once in a while, the field is plucked and an electron comes out. But otherwise, there's no feeling of the electron field. The Higgs field is unique and special, and it is everywhere non-zero. Okay? It's similar to the ether that people talked about in the 19th century. But the difference is that this is a correct ether, not an incorrect ether. Okay? So this is a correct ether. Okay, so this is okay. So now we're going to mix the metaphor a bit, and so there's a mist, and it goes everywhere, and it's hard to talk about things moving through this mist, but it's sluggish moving through this non-zero mist of water. So it has slugga going through it, and that is mass. All right. So the Higgs field is the only field that we know of that has non-zero value all throughout space. And it was postulated in the 1960s, mid-1960s, by Higgs, Brout, and Englert, some 40 years ago, but I guess 50 years ago now or so, that elementary particles get their mass by propagating in this Higgs mist, this Higgs field. And different masses arise by different couplings to this background Higgs field. Okay, so there's technical mathematics of how you can show this, but it's basically some things are able to wade through the water faster than other things. And if you're at the beach, you see some people are able to wade through the water faster than other people. And this is the metaphor for how the Higgs works. Massive particles plowing through thick water, the Higgs field. And this is the metaphorical explanation for the Higgs field. And the metaphor is not too far off from how we actually think about it as physicists. That this is what we have in mind when we think about the Higgs field, permeating everything. So it's not just an empty metaphor dreamed up for the purposes of telling people in the newspaper, but we actually think along those lines as well. Now, this is Peter Higgs and the maths. This is a picture I got from the University of Edinburgh. When I was in Europe, University of Edinburgh asked me to come to Edinburgh and give a colloquium. And I said, that's great, and what would you like the colloquium to be about? And they said, about the Higgs boson. I said, well, this guy's there. He's, he's the one that, he's the one that you know, figured it all out. And they said, yeah, it's okay. He might come to your talk. So I went there and I gave the talk, and it all went fine, and he didn't give me a problem, which was nice of him. So this is the mathematics, okay? And I like the chalkboard because the chalkboard sort of looks like that mist a couple of slides ago. But this is the mathematics, and our education in physics has a lot of what we do is tied up in what's on this chalkboard. Our calculus, you need to know calculus really well to know this first letter, D, capital D, okay? And this subscript, that's a mu, that's a Greek letter mu. This subscript, the students have to know special relativity very well to understand what that means. This phi, that's the field. This is a description of this mist, this field, all throughout the universe. You need to know quantum mechanics well to know what this is, and you need to know quantum field theory, so the field thing. This star, you need to know the mathematics of complex analysis for that star. The minus sign, you have to pay attention in 3rd grade, okay? So if we have a student that has trouble with that, then we really have to start over again, but luckily, there's very few students that have that trouble. So there's so much wonderful physics and mathematics that is tied up in this, and the students love it, and it's just a great achievement of humankind that we pieced all these different elements of knowledge together, and we were able to come up with this speculation. But it was a speculation, okay? And as with all speculations, you've got to figure out how to prove it. If you're a scientist. If you're not a scientist, you don't have to worry about proving it. You can just live by it. But as a scientist, you have to prove it. So we have this Higgs field everywhere. All right? Sounds mysterious. How are we going to gain access to it? How are we going to figure out that it's there? So what we do is we look for the Higgs particle. So there's a distinction between Higgs field and Higgs particle. There's only one Higgs field. The field permeates all of the universe. But you can pluck the field in various places. It's like a pebble dropping in the water, and then a wave coming out. And that wave is, you can talk about it. It's something coherent that you can talk about, this wave. And so we talk about that as a particle, and that's what a particle does. It's a wave perturbation in the field. And you can have many different pebbles dropping, many different waves dropping. So you can have an electron here, you can have an electron at Ypsilanti, you can have one in Paris, and these are excitations, small pluckings of the electron field. The same thing can happen for the Higgs. There's a Higgs field, so we should find a way to pluck the Higgs field and make a Higgs particle. Now, you can't just pluck it anywhere. You have to, I can't just make it by doing that. I have to collide very high energy particles together, because the speculation is that it's a rather heavy mass object. So you need a lot of energy to smash into each other, particles, and pluck the Higgs field and make a Higgs particle. So that's the next goal. You have to make the Higgs particle to prove this wild speculation that these people made some years ago. So who's going to do it? CERN said, we'll do it. Okay? The United States said, we'll do it, but then Congress said, no, we won't. But in Europe, they said, we'll do it. And so it was built, a 27-kilometer circumference ring in Geneva. This is the Geneva airport right there. That's Lake Geneva. And colliding proton beams went around this collider in opposite directions and collided at various points along this tunnel. And you probably saw reports about the end of the universe is going to come because they're colliding things at such high energy that it will make black holes and we'll all die. Well, the way you can disprove that is all the physicists that made it all live around here. Okay? Now, if the newspapers found out that all physicists lived in deep bunkers behind the mountains here, then they should have been worried. But we all lived around here, so it's all okay. And they collided those protons at extremely high energy. And if you make a Higgs boson, it's like a tree falling in the forest. If there's nobody to detect it, then you don't know what happened. So we have to make a detector to see it. Well, this is such high energy that we make this huge detector. My colleagues, my experimental colleagues at the university, worked on a detector called the Atlas detector that was installed at CERN along the beam. And this is the size of a person. So, and the detector is really high, really big, very tall. I saw it in person, and it's overwhelming in person to see it. And even on a picture, I think it's somewhat overwhelming. And you need all this material because when you collide protons coming from that direction and protons coming from this direction, it makes highly energetic particles that somehow need to be stopped. And you need a lot of material to detect it and stop it and measure it, what energy it has. So the collisions happened right there. The Higgs boson was made, or that's what they were hoping for, that it'd be made right there. And then particles come out and are detected with all this instrumentation. So this is one way to make a Higgs boson. So protons coming from the left here, and a proton's coming from the right. And they're going very fast towards each other on a collision course. And inside the proton, there are quarks and gluons and other things. And one good way of producing the Higgs boson is to take one gluon out of the quark coming from the left and take a gluon coming out of the proton coming from the right and smashing those constituents. So the big proton is a big lumbering spaceship as far as this is concerned, this collision is concerned. And the only things that are colliding are individual constituents. That's the collisions that we're looking for. So the gluon from one proton, the gluon from another one, they collide. And in that collision, there's quantum effects that are happening. So out of the vacuum pops a top quark. Just briefly, a top quark comes, it interacts with these gluons, and it enables the construction of a Higgs boson. So the collision happens, there's a quantum mechanical production of the top quark, which then goes into a Higgs boson. So the Higgs boson lives for a very brief time. It's born. You know, it stretches and says, here I am, I'm born. And then it immediately dies. It dies so quickly that it doesn't even propagate a discernible distance in the detector. So in this detector, it's born right there and it dies right there. It's like a few of my relatives. They're born in one spot and they die right there because they don't want to leave. And this is how the Higgs boson is. Immediately dies, and then it decays. So when it dies, When a particle dies, it's another way of saying it decays into other things. So the Higgs boson can decay into many different things. And there's quantum mechanical probabilities of the different things it can decay into. And one of the things it can decay into is a photon. It's 2 photons. So the Higgs is born, and then through some quantum loop of a W boson, it decays into 2 photons, which is 2 very high energy rays of light. And this is how we physicists write down this picture. We say PP to glue, to PP is proton, to gluon, to Higgs boson, to 2 photons. The energy of these 2 photons, remember Einstein's equation. The energy of these 2 photons, when added together and then multiplied by this speed of light prefactor, it gives you what's called an invariant mass of the 2 photons. So you equate it with a mass. And because energy is conserved, there's no, all energy doesn't just leave the universe, it's conserved. This mass that is made up of this energy is equivalent to the Higgs boson mass. So the whole game is to look for 2 photons coming out, hitting the detector. So 2 photons live a long, long time, right? So they can come and they smash the detector here, and you measure their energies, and then you sum their energies, and then you say, well, if the Higgs boson exists, that energy must be the mass of the Higgs boson. So this is what they did. They looked for this 2 photon mass in the collider, and they made a plot of all the events they got for different masses. Now, the unfortunate and difficult part of this experiment is that there's many things that can give you 2 photons. And they aren't the Higgs, most of them are not the Higgs boson. They're standard run-of-the-mill things that we understand very, very well. All the stuff happening up here is stuff we understand very well. There's no mystery. Nobody's going to win a Nobel Prize here. And nobody's going to win a Nobel Prize there. The way you win a Nobel Prize is to look for a smooth curve having a bump in it. And that bump happened. More and more data happened. These are the small error bars on the data, these black lines are the small error bars. The more and more data accrued started showing this small bump. And that small bump was centered at 126 GeV, giga electron volts. That's 126,000 MeV. So that's much greater than the proton mass. It's about 130 times greater than hydrogen, the proton mass. So it's very massive, very heavy, and they found this bump. Now, this looks really, it's very scientific. There's a graph, and there's a bump, and you look at it, and after you look at it, this is what happens, okay? This was in the New York Times the day they announced the discovery of the Higgs boson. I'm really angry at the New York Times because I am over here, okay? So I didn't have a friend in the New York Times to put me in the photo. But it was a big party. It was on the 4th of July, which I thought was quite appropriate. And there was, it happened at 9 o'clock in the morning, this meeting. It was, nobody knew, even as a staff member, I'm in the theory group there, not in the experimental group. It was a bit unclear exactly how sure they were that a Higgs boson was discovered. There was still a lot of talk in the lunchroom about, well, maybe it's not a Higgs. It could be fluctuations, statistical fluctuations, we don't know. And they called this big meeting at CERN to give an update on the Higgs search. That's how they phrased it, updated on the Higgs search. I thought, okay, that's fine. And then I got an email from the head of the division saying, would you like a ticket to go to it? I said, a ticket? I mean, I normally don't get a ticket to go to a physics doc. It must be kind of important. I said, sure, I'll have a ticket. And so the talk was at 9. And I take the bus to CERN, and I get off, and I'm walking through the hallways, and there's this line that's going all down the corridor from the auditorium all the way down to the main office buildings of CERN. I thought, wow, this is, and there was one good friend of mine who's 6 months pregnant who was standing in line since 5:30 in the morning to try to get in, because this is how big of an event this was. And people sort of the day before started understanding this is going to be a really big event. And so I was fortunate to be in there. They announced that a discovery indeed had been made, and it was really exciting. The New York Times snapped this photo. There was an article about it on July 4th. It was posted that very night in the New York Times. And so then the news media got very excited, right? We found it, we found it, found it. And then suddenly, all of us at CERN started getting phone calls from reporters saying, by the way, what is it that you found? So suddenly we're put in the position of we have to explain this to reporters who have very little scientific background. So I was, since I'm a native English speaker, I was on the phone with American reporters and British reporters, and I had colleagues who were on the phone with other people. And over the next few days, different reports started coming out about the explanation of the Higgs boson. And I had one friend who was just completely distraught. He said, oh, I had this, they quoted me in this article, and the reporter just completely botched it. I'm so embarrassed. I walk down the halls at CERN. They're gonna think I gave them a wrong explanation and so on. And I said, really, you should calm down, because very few people know Croatian. So it's it's not going to be a problem. You know, the few Croats, you need to, you know, talk to them, but for the rest of us, it's going to be okay. And so I had an exchange with somebody in the New York Times about this, and a few days later, an article came out about the Higgs boson. So it was an exchange with Christopher Buckley. Many of you know who Christopher Buckley is, right? And I knew that something was maybe a bit fishy, because he sent me an email the night before it came out that said, sorry, James, I couldn't resist. I thought, I wonder what that is. So here's the article. Sunday Review. If you've seen the New York Times Sunday Review with Christopher Buckley, he said, the Higgs boson and you. So the first question, everybody, this is 3 days after the discovery. What exactly is a Higgs boson? Why all the fuss? Okay, the first answer is already sort of alarming. Essentially, it's an teensy-weensy particle, we're talking small here, that contains the answers to how the universe came about, including whether God was involved. Okay. And this was not even in Croatian. Okay, so, and it's the New York Times, and I just wrote back and I said, thank you for not citing me. So I would have been able to walk down the halls at CERN. So that he's a really funny man. It was a really funny article and great. And then some months later, Time magazine said, you know, let's make it Time Person of the Year. And you know, what do you think of this? And the person who wrote the article said all kinds of interesting things, but I have highlighted on the bottom that apparently the discovery of the Higgs boson finally fully confirmed Einstein's general theory of relativity, which it doesn't do. But we're happy to have the press, and I think the thing that most surprised us is that the answer to the question, should the Higgs boson be Times Person of the Year in 2012, 20% of the people said definitely. So, I mean, well, 20% of the people, that's wonderful. I mean, we made great headway into popular culture. So this has been really an extraordinary achievement of the human creativity. This was pure speculation in the 1960s, and that speculation turned into careful analysis, and there's much theory that had to go in and much experiment. It is an achievement of the intellect, achievement of perseverance, of organization. I mean, imagine putting 6,000 physicists together, not one of whom thinks they have a boss, and then creating this big event and this big discovery. I think it's extraordinary. But we are still far away from the very roots of the origin of mass. We have made this tremendous progress of understanding the bundle of energy part of mass and the elementary particle mass. New discoveries, as always, lead to new questions that will occupy us for decades and even centuries. And some of the questions that we face are, is it really the Higgs boson? So measurements are always tentative. You never have metaphysical certainty of anything that you're measuring. You only get better and better at understanding what you have. And right now, the uncertainties on the couplings of this Higgs boson to standard model particles is of order of 30%. Metaphysical certainty requires 0% uncertainty. We have 30% uncertainty on the couplings. But it's really walking like a duck and quacking like a duck, and I think it is a duck. But there's still lots of questions, and many theories tell you that there should be ever so tiny differences between what was found and the pure standard model Higgs boson that was postulated a few decades ago. Another question which occupies us a lot is how can the Higgs boson be stable to quantum corrections? There's something very unique about it. It is the only pure spinless elementary particle that we know about. And if you were asked scientists 10 years ago, can a pure elementary particle exist that is spinless, about a quarter of them would say no possible way. They're unstable to quantum corrections, and their mass cannot be as light as people are postulating it to be. So in order to make it stable, it needs an entourage. It needs other particles to support it and keep it at its mass of 126 GeV and not quantum mechanically go unstable to a much higher mass. So this is occupying many of us in the theoretical community to try to understand that. Also, it has introduced a brand new problem in physics, and it's what I call Lagrangian mass. So there's the bundle of energy Einstein mass, there's the elementary particle mass that we talked about today. The Higgs boson now has introduced a new mass problem, which I call the Lagrangian mass. And it is, in this picture of Mr. Higgs, it is, well, you can't see it, but it's basically this alpha right there. In fact, I think it's interesting, it looks like he erased it and then wrote it again. It's this parameter right here that causes nightmares to particle theorists like me, okay? And keeps us up at night and try to explain it. Okay, so now the final thing is that everything I've talked about today is less than 0.4% or 3%, depending on how you want to count it, of the universe. Most of the mass or energy of the universe that we see is in dark energy, and then 23% of the energy of the universe is in the form of dark matter, which is probably another elementary particle which gets mass. And it is unlikely that it gets mass through the Higgs boson. And how it gets mass and why it gets mass is another case of pure speculation. Just as we had pure speculation in the 60s that worked out and we made discoveries today, maybe in 40 years, all of our speculations that we're deriving and trying to figure out about dark matter, maybe in 40 years we'll know that that is correct, and then a whole new set of questions will come about. So there's still many more things to discover and understand in the decades to come about mass. Okay, thank you.